Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the alien mathematics of the 3i Atlas system, three worlds that dance around their star in ways that quietly break the rules we thought governed all planetary motion. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Deep in the constellation Atlas, 47 light-years from Earth's patient orbit, three planets move through space in a gravitational ballet that should not exist. They circle their young star in perfect resonance for every 2 orbits the innermost world completes. The middle planet completes exactly 3, while the outermost world traces a single, stately revolution. This mathematical precision emerges from chaos theory's predictions like a whispered impossibility, each world pulling and tugging at its companions in ways that create stability from what should be destruction. The resonance holds with a precision that makes atomic clocks seem sloppy. Over millions of years, not a single orbital period has drifted by more than a few minutes. This clockwork perfection puzzles astronomers because resonant chains typically form through slow, careful migration planets gradually spiraling inward through their star's protoplanetary disk, their orbits naturally falling into mathematical harmony. But 3i Atlas accomplished this feat in mere hundreds of thousands of years, around a star barely old enough to have cleared the dust from its stellar nursery. The star itself burns with the fury of youth, its surface temperatures fluctuating by hundreds of degrees as stellar storms rage across photospheric plains larger than Jupiter's great red spot. Magnetic field lines twist and snap, launching coronal mass ejections that would strip away the atmospheres of any normal planetary system. Yet the 3 worlds of 3i Atlas maintain their atmospheric envelopes as if protected by some invisible shield, their orbital dance continuing undisturbed through magnetic tempests that should have rendered them airless, lifeless rocks billions of years ago. Each planet maintains an orbital eccentricity so low that their paths around the star trace nearly perfect circles. This geometric precision defies the gravitational chaos that typically characterizes young planetary systems, where worlds migrate, collide, and scatter like billiard balls struck by an angry god. The inner planet completes its orbit in 4.2 Earth days, its surface temperature locked in perpetual twilight as tidal forces have synchronized its rotation with its revolution. The middle world takes 6.3 days to circle the star, while the outer planet requires 12, 6 days each period, a perfect mathematical multiple of the others. Computer simulations run backwards through time cannot reproduce the system's formation. Every model that creates the observed resonance also predicts collisions, ejections, or orbital decay that never occurred. The gravitational interactions between 3 massive worlds in such close proximity should produce chaotic dynamics, with orbital periods gradually shifting until the resonance breaks and the system falls apart. Instead, 3i Atlas demonstrates a stability that extends millions of years into the past and, according to dynamical models, millions more into the future. The mystery deepens when astronomers examine the system's angular momentum distribution. In our solar system, the Sun contains 99.8% of the system's mass, but only 0.5% of its angular momentum. Most of the rotational energy resides in the orbital motion of the planets, particularly Jupiter. This distribution tells the story of planetary formation, migration, and gravitational interactions spanning billions of years. But 3i Atlas shows an angular momentum distribution that matches no theoretical model, as if the planets and star formed from fundamentally different processes than anything observed elsewhere in the galaxy. The star's rotation period of 7 hours creates magnetic field geometries that should tidally lock the inner planet while destabilizing the orbits of the outer worlds. Instead, the inner planet spins once every 4.2 days, exactly matching its orbital period in perfect synchronous rotation. While the middle and outer planets maintain rotation rates that correlate with no known tidal theory, the gravitational tides that should gradually slow planetary spins and expand orbits appear to operate under different physical laws in the 3i Atlas system. Transit observations reveal planetary sizes and masses that place all three worlds in the category astronomers call super-Earths, too large to be terrestrial, too small to be gas giants, with densities that suggest compositions intermediate between rock and ice. These measurements carry uncertainties that would normally provide comfortable margins for theoretical interpretation. But every possible composition model for planets of these sizes and masses requires formation scenarios that contradict the system's observed youth and orbital architecture. The planets maintain their impossible dance with the patience of geological time, each world precisely where it should not be, moving exactly as it should not move. Radio telescopes detect faint emissions from the system at frequencies that suggest complex electromagnetic interactions between the planetary magnetospheres and their star's variable magnetic field. These signals pulse with periodicities that match neither the planetary orbital periods nor the stellar rotation, hinting at electromagnetic processes that current plasma physics cannot fully explain. Only took a few hundred millennia to make a mockery of our best theories about planetary formation timescales. Only required 3 small worlds to challenge fundamental assumptions about gravitational dynamics. Only needed perfect orbital resonance to whisper that the universe operates by rules more subtle and strange than human mathematics has yet discovered. Sometimes, the universe whispers its secrets in frequencies we have not yet learned to hear. The 3i Atlas system continues its ancient dance, each orbit a quiet revolution against the comfortable certainties of planetary science, each transit across the star's face a gentle reminder that cosmic truth often wears the patient mask of impossibility. The star at the heart of the 3i Atlas system burns with an adolescent fury that should have already written the obituary of any planetary companions. At barely 2 million years old, an infant by stellar standards, it radiates energy across the electromagnetic spectrum with the unpredictable violence of youth. Its surface churns with magnetic storms that dwarf anything our own sun produces, launching coronal mass ejections with energies equivalent to billions of hydrogen bombs detonating every second. Stellar flares erupt from its photosphere with temperatures exceeding 20 million Kelvin, creating brief moments when the star outshines itself by factors of 10 or more. Yet around this stellar tempest, 3 worlds formed and achieved orbital stability in a time frame that challenges every model of planetary accretion. Current theory suggests that terrestrial planets require 10 to 100 million years to assemble from the slow gravitational accumulation of planetesimals, rocky debris left over from stellar formation. The process begins with microscopic dust grains sticking together through electrostatic forces, gradually building into pebbles, then boulders, then kilometer-sized bodies that eventually collide and merge into planetary embryos. In the 3i Atlas system, this entire sequence must have occurred while the star was still contracting from its initial gravitational collapse, its luminosity varying by orders of magnitude as it settled into stable hydrogen fusion. The protoplanetary disk of gas and dust that gave birth to these worlds would have been bombarded by stellar winds powerful enough to strip away volatile materials and scatter small particles into interstellar space. Somehow, despite this cosmic sandblasting, solid matter accumulated into planetary cores and retained enough mass to gravitationally capture substantial atmospheres. The rapid formation timeline becomes even more puzzling when astronomers consider the isotopic ratios detected in the planetary atmospheres. Spectroscopic analysis reveals abundances of heavy elements that typically require multiple generations of stellar nucleosynthesis to produce. These isotopes should not exist in such concentrations around such a young star, unless the planets formed from materials that had traveled vast distances through the galaxy before settling into the 3I Atlas system. The chemical signatures suggest a cosmic migration story that spans hundreds of millions of years, yet the planets themselves show no signs of the atmospheric erosion that should accompany such ancient wandering. The central star's variable luminosity creates a habitable zone that shifts inward and outward like a cosmic tide, sometimes encompassing all three planets, sometimes none. During stellar maximum, when magnetic reconnection events trigger massive flares, the star's energy output increases by factors of 3 to 5, pushing the habitable zone far beyond the outermost planet's orbit. During quiet periods, the reduced stellar radiation allows ice to form on all three worlds simultaneously. This cyclical heating and cooling should create atmospheric instabilities that destroy weather patterns and prevent the establishment of stable climate systems. Instead, each planet maintains atmospheric conditions that appear remarkably constant over timescales of thousands of years. The inner world shows no signs of atmospheric stripping, despite receiving stellar radiation doses that would boil away Earth's oceans in mere centuries. The middle planet maintains cloud patterns that persist through multiple stellar activity cycles, while the outer world exhibits seasonal variations that correlate with its orbital position rather than the star's unpredictable energy output. The star's youth means that its rotation rate and magnetic field strength continue to evolve on timescales of millennia rather than millions of years. Young stars typically spin faster and generate stronger magnetic fields than their mature counterparts, creating electromagnetic environments that vary dramatically over short periods. The 3I Atlas star shows rotational periods that have decreased by nearly 10% over the past 1,000 years of observations, yet the planetary orbits show no corresponding changes in their resonant relationships. This temporal disconnect suggests that the gravitational interactions between the planets create a dynamical system more stable than the star-planet interactions that typically dominate young planetary systems. The three worlds appear to have achieved a state of collective equilibrium that insulates them from the chaos of their stellar environment, like a gravitational choir that continues singing in perfect harmony despite the discordant solo of their temperamental conductor. Stellar evolution models predict that the 3I Atlas star will continue brightening and stabilizing over the next 50 million years as it settles into main sequence hydrogen burning. During this period, most young stellar systems lose their initial planetary companions to gravitational scattering, atmospheric erosion, or tidal disruption. The fact that three massive planets survived the violent birth throes of their star suggests either extraordinary luck or physical processes that current astrophysics does not fully understand. The mystery deepens when astronomers examine the star's chemical composition. Stellar spectroscopy reveals abundances of lithium, beryllium, and other light elements that should have been destroyed by nuclear reactions during the star's pre-main sequence contraction. These elements serve as cosmic chronometers, their presence indicating stellar ages much younger than the apparently mature planetary system they illuminate. The chemical clock of the star disagrees with the dynamical clock of the planets by factors of 10 or more. Only took 2 million years to assemble what should require 50 million. Only needed perfect timing to coordinate planetary formation with stellar evolution in ways that defy statistical probability. only required a young star to nurture mature worlds, while simultaneously trying to destroy them with adolescent rage. The star continues its violent youth while its planetary children dance their ancient dance. Each solar flare, a reminder that cosmic nurseries operate by rules more complex than human theories have yet imagined. In the gentle mathematics of orbital resonance, 3 worlds find stability around a star too young to permit their existence, too chaotic to allow their survival, too alien for our current models to explain. The innermost world of the 3i Atlas system possesses a density that places it in the theoretical no-man's land between rocky terrestrial planets and gaseous mini-Neptunes. At 1.7 times Earth's radius and 3.2 times Earth's mass, it should classify clearly as either a super-Earth with a substantial rocky core or a sub-Neptune with a thick hydrogen-helium envelope. Instead, its bulk density of 4. 1 grams per cubic centimeter suggests a composition that exists nowhere else in the known universe, too dense for a gas-dominated world, too light for a purely rocky planet. This density anomaly represents more than a simple measurement uncertainty. Repeated observations using multiple techniques, transit photometry, radial velocity measurements, and gravitational microlensing all converge on the same impossible value. The planet contains mass equivalent to 3 Earths compressed into a volume that should accommodate only 2.5 Earths worth of rock and metal. The missing volume cannot be explained by atmospheric compression, core mantle differentiation, or any known planetary structure model. Theoretical compositions that might produce such densities require exotic states of matter, typically found only in the cores of white dwarf stars or the crusts of neutron stars. At the pressures and temperatures expected in a planet of this size, normal rock and metal cannot achieve the required compression. Some models propose cores composed of metallic hydrogen or degenerate matter. But these phases require pressures millions of times greater than anything possible in planetary interiors. The density suggests physics beyond the standard model of condensed matter. The planet's gravitational field exhibits subtle anomalies that compound the mystery of its internal structure. Precise tracking of spacecraft trajectories during hypothetical flybys, calculated from the observed orbital perturbations of its companion worlds, reveals gravitational moments that indicate mass distributions fundamentally different from terrestrial planets. The gravitational signature suggests a core that occupies nearly 80% of the planet's radius, surrounded by a mantle so thin it challenges the basic mechanics of planetary differentiation. On Earth, the iron-nickel core comprises roughly 30% of the planet's radius, with the remaining volume occupied by silicate mantle and a thin crustal shell. This structure arose from billions of years of gravitational settling, with dense metals sinking toward the center while lighter rocks floated upward. The 3i Atlas inner planet appears to have inverted this process, concentrating nearly all its mass in a central region while maintaining a low-density outer shell that should have collapsed under its own gravity eons ago. The planet's surface shows no signs of the geological activity that should accompany such an unusual internal structure. Thermal infrared observations detect surface temperatures that vary smoothly with stellar illumination, indicating efficient heat distribution through atmospheric circulation. There are no hotspots, volcanic emissions, or tectonic signatures that would mark the release of gravitational potential energy from ongoing core contraction or mantle convection. The world appears geologically dead despite possessing an internal structure that should generate enormous amounts of heat. Atmospheric spectroscopy reveals a chemical composition dominated by water vapor, carbon dioxide, and methane molecules that should exist only as ices at the planet's distance from its star. The atmospheric pressure exceeds 10 Earth atmospheres, Yet the observed molecular absorption lines suggest temperatures and densities that cannot coexist under normal thermodynamic conditions. The atmosphere behaves as if governed by an equation of state that differs subtly but fundamentally from terrestrial physics. The planet's magnetic field strength, inferred from radio emissions and interaction with stellar wind, indicates a magnetosphere comparable to Jupiter's, despite the world's much smaller size and presumably solid composition. Magnetic field generation typically requires convection in a liquid metallic core, but the inferred core composition and structure should not permit the fluid motions necessary for dynamo action. The magnetic field exists without an apparent mechanism for its generation, persisting at strengths that should decay in mere thousands of years without continuous regeneration. Transit observations reveal atmospheric features that change on timescales of hours rather than the days or weeks typical of planetary weather systems. Cloud formations appear and disappear with periodicities that match neither the planet's rotation period nor its orbital motion around the star. These rapid atmospheric dynamics suggest energy sources beyond solar heating and tidal flexing, perhaps gravitational interactions with its companion worlds or electromagnetic coupling with the stellar magnetic field. The planet's rotation period remains precisely synchronized with its orbital period, maintaining perfect tidal locking despite gravitational perturbations from its companion worlds that should gradually decouple rotation from revolution. This synchronous state requires continuous fine-tuning of the planet's rotational energy, yet no mechanism exists for the necessary energy dissipation or redistribution. The planet spins at exactly the right rate to keep one face perpetually pointed toward its star, as if cosmic forces conspired to preserve this geometric perfection. Stellar occultation measurements during planetary transits reveal atmospheric layers with refractive indices that change abruptly at specific altitudes, creating optical effects that suggest discrete changes in atmospheric composition or phase. These layered structures resemble the stratospheric boundaries found in gas giant atmospheres, but they appear in a world whose mass and size should preclude such complex atmospheric architecture. The observations hint at atmospheric physics operating under conditions that current models cannot reproduce. Only took 3 Earth masses to challenge everything we know about planetary interiors. Only needed perfect tidal locking to raise questions about rotational dynamics that have guided celestial mechanics for centuries. Only required one impossible density to suggest that matter behaves differently in the alien environment of the 3I Atlas system. The innermost world continues its rapid orbit. Each revolution a quiet demonstration that planets can exist in states that transcend the comfortable categories of terrestrial and gaseous, rocky and volatile, possible and impossible. High above the surface of the middle planet, clouds of vaporized iron drift through an atmosphere that should not exist. Spectroscopic analysis reveals absorption lines characteristic of gaseous metals, iron, magnesium, silicon, and aluminum suspended in atmospheric layers where temperatures barely exceed 800 Kelvin. At such relatively cool conditions, these elements should condense into solid particles and rain down to the surface within hours or days. Instead, they maintain their gaseous state for months at a time, forming persistent cloud formations that stretch across hemispheres and persist through multiple orbital cycles. The metallic vapors exhibit circulation patterns that defy conventional atmospheric dynamics. Instead of following the pressure gradients and temperature differences that drive weather systems on terrestrial worlds, the metal clouds move in spiral formations that correlate with the planet's magnetic field lines. Iron vapor streams flow along invisible magnetic highways, creating atmospheric rivers of vaporized metal that span thousands of kilometers while maintaining coherent structure for weeks at a time. These magnetic weather patterns suggest atmospheric processes that operate more like plasma physics than meteorology. Earth's atmosphere contains trace amounts of metallic vapors, sodium from meteor ablation, iron from cosmic dust, but these constituents comprise less than 1 part per billion of the total atmospheric mass. The 3I Atlas middle planet maintains metal vapor concentrations that exceed Earth's levels by factors of millions, creating an atmosphere where gaseous metals contribute significantly to atmospheric pressure, opacity, and thermal properties. The sheer abundance of vaporized metals implies surface processes that continuously replenish atmospheric metallic content against gravitational settling and chemical condensation. The source of these metallic vapors remains a profound mystery. Volcanic outgassing typically produces water vapor, carbon dioxide, and sulfur compounds, but rarely generates significant quantities of vaporized metals. Impact events from asteroid or comet collisions can briefly inject metallic vapors into planetary atmospheres, but such transient phenomena cannot sustain the observed concentrations over geological timescales. The planet shows no signs of ongoing volcanic activity, recent impact cratering, or surface processes capable of vaporizing metals at the observed rates. Some theoretical models propose that intense stellar radiation could heat surface rocks to temperatures sufficient for metal sublimation, but the 3I Atlas middle planet receives only modest stellar flux comparable to Mars's solar heating. The required surface temperatures would demand greenhouse heating mechanisms that far exceed the warming potential of conventional atmospheric gases. Alternative proposals invoke exotic heating sources, radioactive decay from unusually heavy isotopes, tidal heating from gravitational interactions with companion planets, or electromagnetic heating from coupling with stellar magnetic fields. The metallic clouds exhibit optical properties that create atmospheric phenomena unknown in terrestrial meteorology. Iron vapor clouds scatter visible light with wavelength dependencies that produce spectacular atmospheric displays, sunsets that shift through the entire visible spectrum as different metals absorb and re-emit photons at characteristic frequencies. Magnesium clouds create silvery reflective layers that act like atmospheric mirrors, while aluminum vapors generate iridescent formations that shimmer with colors that have no names in human language. Atmospheric circulation models struggle to explain how gaseous metals remain suspended against gravitational settling. Metal atoms are typically dozens of times more massive than the hydrogen, helium, and molecular gases that dominate planetary atmospheres. Conventional atmospheric dynamics predict that such heavy constituents should settle toward the surface within planetary rotation periods, creating stratified atmospheric layers with metals concentrated in dense, low-altitude clouds. Instead, the metallic vapors maintain nearly uniform distributions throughout the observable atmosphere. The magnetic field interactions that guide metal vapor circulation require electromagnetic coupling strengths that exceed theoretical predictions by orders of magnitude. Gaseous metals in planetary atmospheres typically exhibit weak responses to magnetic fields because thermal motion randomizes particle velocities and prevents coherent electromagnetic behavior. The organized, field-aligned flows observed in the 3I Atlas system suggest that the metallic vapors behave more like magnetized plasma than ordinary atmospheric gas, despite temperatures and pressures that should preclude plasma formation. Spectroscopic monitoring reveals that the metallic cloud compositions change with planetary orbital position, as if the atmosphere responds to varying stellar radiation or gravitational influences from companion worlds. During closest approach to the star, iron and magnesium concentrations increase, while aluminum and silicon levels decrease. Near orbital aphelion, the trend reverses, creating seasonal variations in atmospheric metal content that follow no known pattern of stellar heating or gravitational perturbation. The planet's atmospheric mass exceeds theoretical predictions for worlds of its size and stellar distance by factors of 3 to 5. Standard models of atmospheric retention predict that planets in the 3I Atlas system should have lost most of their gaseous envelopes to stellar wind stripping and thermal escape within the first few million years of their existence. The persistent, metal-rich atmosphere suggests either continuous atmospheric replenishment from unknown sources or atmospheric retention mechanisms that operate beyond the scope of current planetary science. Radio observations detect electromagnetic emissions from the planet at frequencies characteristic of cyclotron radiation, the telltale signature of charged particles spiraling along magnetic field lines. The emission pattern suggests that some fraction of the atmospheric metals exists in ionized form, creating a tenuous ionosphere composed of metallic plasma rather than the hydrogen and helium ions found in terrestrial upper atmospheres. This metallic plasma layer could provide the electromagnetic coupling necessary to organize atmospheric circulation along magnetic field lines. Only took vaporized metals to rewrite atmospheric science textbooks. Only needed impossible weather patterns to suggest that planets can sustain atmospheric processes that terrestrial physics cannot explain. Only required persistent metal clouds to whisper that the universe operates atmospheric systems beyond the comfortable boundaries of earthly meteorology. The middle planet continues its stately orbit, metallic clouds streaming through its alien atmosphere like rivers of light. Each spectroscopic observation a gentle reminder that cosmic weather systems follow rules more subtle and strange than human theories have yet discovered. Radio telescopes across Earth detect a symphony of electromagnetic signals emanating from the 3I Atlas system, not the random static of cosmic background radiation, but organized pulses that repeat with mathematical precision while following no pattern that human physics can decode. The signals arrive at frequencies ranging from 30 MHz to 3 GHz, covering the same radio spectrum used for terrestrial communications. Yet their structure suggests sources and mechanisms that operate by entirely different principles than any known astrophysical phenomenon. The radio emissions pulse with periodicities that correlate weakly with the planetary orbital periods, but never quite match them exactly. The strongest signals repeat every 23 Earth days close to the inner planet's 4.2-day orbit, but offset by precisely 43 minutes in a pattern that remains constant across years of observation. Secondary emission peaks occur every 6.31 and 12.64 days, again approaching but never exactly matching the middle and outer planet's orbital periods. These slight discrepancies suggest that the radio sources move independently of the planets themselves, perhaps linked to atmospheric or magnetospheric phenomena that drift slowly relative to planetary motion. Each planet in the system generates its own distinct radio signature, but the individual emissions interact and interfere with each other in ways that create complex beating patterns and harmonic resonances. When the planets align in their orbital dance, their combined radio output sometimes amplifies to intensities that exceed the sum of individual contributions by factors of 10 or more. During other orbital configurations, the signals partially cancel each other, creating radio quiet periods that last for days before the electromagnetic chorus resumes its alien song. The magnetic field interactions that generate these radio emissions defy conventional plasma physics models. On Jupiter, similar radio signals arise from charged particles accelerating along magnetic field lines, creating cyclotron radiation as electrons and ions spiral through the planet's magnetosphere. But the 3I Atlas signals exhibit polarization characteristics and frequency distributions that suggest particle acceleration mechanisms operating at energies and magnetic field strengths impossible for planets of the observed sizes and masses. Detailed analysis of the radio spectrum reveals fine structure that hints at electromagnetic processes more complex than simple synchrotron or cyclotron radiation. The signals contain frequency modulations that repeat on timescales of minutes to hours, creating what radio astronomers describe as electromagnetic chirps, rapid frequency sweeps that rise and fall in pitch like cosmic bird songs. These chirping patterns occur simultaneously across widely separated frequency bands, suggesting coherent emission processes that coordinate electromagnetic activity across vast ranges of the radio spectrum. The magnetic field configurations necessary to produce such organized radio emissions require planetary magnetospheres with geometries that current dynamo theory cannot explain. Standard models predict that planets generate magnetic fields through convection in liquid metallic cores, creating dipolar field structures similar to bar magnets with north and south poles. The three-way atlas radio signatures suggest magnetic field topologies that include quadrupolar, octupolar, and higher-order components, complex field geometries that typically arise only in rapidly rotating stars or exotic astrophysical objects. Computer simulations that attempt to reproduce the observed radio patterns require magnetic field strengths exceeding those of Jupiter by factors of hundreds to thousands. Such intense magnetic fields would demand planetary cores composed entirely of superconducting materials or exotic matter states that remain stable under planetary interior conditions. The energy requirements for maintaining these electromagnetic fields exceed the total gravitational binding energy of the planets themselves. Yet the radio emissions continue year after year with no signs of weakening or decay. The radio signals exhibit properties that suggest they propagate through interplanetary space by mechanisms more efficient than ordinary electromagnetic radiation. Signals from the outer planet reach Earth with intensities that require impossible transmission efficiencies, as if the radio waves experience amplification rather than attenuation during their journey through the interstellar medium. Some theoretical models propose that the three-eye atlas system generates coherent radio emission through maser or laser-like processes, creating electromagnetic beams that maintain their intensity across interstellar distances. Polarization measurements reveal that the radio waves possess circular and linear polarization characteristics that rotate and evolve during propagation in ways that suggest interaction with structured magnetic fields extending far beyond the planetary orbits. The polarization signatures indicate that the entire three-eye atlas system sits within a large-scale magnetic environment, perhaps a cosmic magnetic bubble that confines and organizes electromagnetic activity across scales ranging from planetary magnetospheres to interstellar space. The temporal evolution of the radio emissions suggests that the electromagnetic environment of the three-eye atlas system changes on timescales that correlate with no known astrophysical processes, over periods of months to years. The signal intensities and frequency distributions drift gradually in patterns that repeat with periodicities of decades. These long-term variations might reflect slow changes in planetary magnetic fields, orbital dynamics, or interactions with the stellar magnetic environment. But the observed time scales match no theoretical predictions for planetary electromagnetic evolution. Attempts to decode the radio signals using pattern recognition algorithms and information theory techniques reveal statistical structures that resemble organized communication more than random astrophysical noise. The signals contain embedded periodicities, frequency correlations, and amplitude modulations that exhibit complexity measures comparable to human language or music. While these patterns likely arise from natural electromagnetic processes rather than artificial intelligence, their organized structure suggests physical phenomena that operate by principles more subtle than current electromagnetic theory encompasses. Only took impossible magnetic fields to challenge fundamental assumptions about planetary dynamo processes. Only needed radio emissions that follow no known pattern to suggest that electromagnetic phenomena in the 3i Atlas system operate by rules beyond terrestrial physics. Only required a broken symphony of cosmic signals to whisper that the universe generates electromagnetic music in frequencies and harmonies that human science has yet to understand. The radio signals continue their alien broadcast. Each pulse and chirp a gentle reminder that cosmic magnetic fields can create electromagnetic phenomena that transcend the comfortable boundaries of plasma physics and planetary magnetism. The orbital paths traced by the three worlds of 3i Atlas carve through space with mathematical precision that violates the NICE model, the theoretical framework that successfully explains the architecture of our own solar system and hundreds of other planetary systems discovered across the galaxy. According to this model, planets form at various distances from their star and then migrate inward or outward through gravitational interactions with leftover planetesimals and gas disk material. The final orbital configuration reflects billions of years of chaotic evolution, with planets scattered, ejected, or settled into stable resonances through slow dynamical processes. The 3i Atlas system shows no evidence of this expected migration history. The planets occupy orbits that appear to have been carved from the vacuum of space with geometric precision, their paths forming perfect ellipses with eccentricities so low they approach the mathematical ideal of circles. The inner planet's orbit deviates from circularity by less than 0.033, a precision that exceeds the measurement accuracy of most astronomical instruments. The middle and outer planets maintain similarly perfect orbital geometries, their paths through space displaying the mathematical regularity of a cosmic clockwork, rather than the scarred trajectories of worlds shaped by billions of years of gravitational chaos. The spacing between planetary orbits follows no known relationship from planetary formation theory. In our solar system, orbital distances roughly follow Titius-Bode relationships, mathematical progressions that reflect the physics of disk accretion and resonant interactions during planetary assembly. The 3i Atlas orbital architecture exhibits spacing patterns that match no theoretical model, with planetary distances that appear chosen to optimize gravitational stability rather than arising from natural formation processes. Each planet maintains orbital inclinations within 0.1 degrees of perfect coplanarity, all three worlds circling their star in the same geometric plane with precision that suggests coordinated evolution rather than independent formation. In typical planetary systems, gravitational interactions and collisional events during formation create orbital inclinations that scatter planets across ranges of several degrees. The 3i Atlas planets move as if guided by invisible tracks that preserve their orbital alignment despite millions of years of gravitational perturbations from their massive companions. The gravitational interactions between the three worlds create what dynamicists call a Laplace resonance, a specific type of orbital harmony where the innermost planet completes exactly 4 orbits for every 2 orbits of the middle planet and every 1 orbit of the outer planet. This 4-2-1 resonance represents one of the most stable possible configurations for a 3-planet system, yet it typically requires millions of years of careful orbital migration to achieve. The 3i Atlas system displays this perfect resonance despite forming around a star barely old enough to have completed its initial gravitational contraction. Computer simulations that attempt to recreate the observed orbital architecture consistently fail to produce stable 3-planet resonances within the required time frame. Models that begin with realistic initial conditions, randomly distributed planetary embryos in a protoplanetary disk, evolve into chaotic configurations with planetary collisions, ejections, or orbital decay. Simulations that artificially impose the observed final state demonstrate that the resonant configuration should remain stable for billions of years. But no known physical process can establish such perfect orbital harmony in mere millions of years. The orbital periods themselves exhibit temporal stability that exceeds theoretical expectations for such a young system. Precise timing of planetary transits across the stellar disk reveals that orbital periods remain constant to within nanosecond precision over observational baselines spanning decades. This temporal regularity suggests that the planets experience no measurable orbital decay from tidal interactions, atmospheric drag, or gravitational wave emission processes that should gradually spiral the worlds inward toward their star over astronomical timescales. Gravitational perturbation analysis reveals that the three planets exchange angular momentum and orbital energy through their mutual interactions in ways that perfectly conserve the system's total dynamical properties. When the inner planet's orbit expands slightly due to tidal forces, the outer planets automatically adjust their motion to compensate, maintaining the overall resonant structure with precision that suggests active feedback mechanisms rather than passive gravitational dynamics. The system behaves as if equipped with a cosmic gyroscope that automatically corrects any deviation from perfect orbital harmony. The absence of observable planetary migration conflicts with direct evidence from the system's debris disk structure. Infrared observations reveal dusty rings and gaps at specific distances from the star that typically mark the gravitational influence zones of migrating planets. These disk features indicate that substantial planetary migration should have occurred. Yet the current orbital configuration shows no signs of the expected migration history. The disk remembers planetary motions that the planets themselves appear never to have experienced. Long-term orbital integration calculations demonstrate that the 3I Atlas configuration represents a profound minimum in the system's gravitational potential energy, a state of maximum stability that would naturally arise if the planets could somehow adjust their orbits to optimize collective gravitational harmony. However, no known mechanism allows planets to actively minimize their potential energy through coordinated orbital changes. The observed configuration suggests that the planet somehow chose the most stable possible orbital arrangement from among countless alternatives. The orbital elements' semi-major axes, eccentricities, inclinations, and resonant angles exhibit correlations that match no statistical distribution expected from chaotic planetary formation processes. The mathematical relationships between orbital parameters appear too perfectly organized to arise from random gravitational evolution, yet too precisely structured to result from any known deterministic process. The orbits suggest underlying order that transcends both chaos and predictability. Only took perfect orbital resonance to challenge decades of planetary migration theory. Only needed mathematical precision to suggest that gravitational dynamics in the 3I Atlas system operate by principles more subtle than Newtonian mechanics predicts. Only required 3 impossible orbits to whisper that cosmic clockwork can achieve precision that exceeds the chaos of normal planetary evolution. The 3 worlds continue their eternal dance, each orbit a gentle revolution against the comfortable assumptions of planetary dynamics, each perfect alignment a quiet demonstration that gravitational harmony can emerge from processes that human celestial mechanics has yet to discover. Across the surfaces of all 3 worlds in the 3I Atlas system, heat flows in patterns that mock every principle of planetary thermodynamics. The inner planet, locked in perpetual tidal embrace with its star, should display extreme temperature contrasts between its day and night hemispheres, the sunward face baked to incandescent fury while the shadow side freezes in absolute darkness. Instead, infrared observations reveal temperature variations of less than 50 Kelvin across the entire planetary surface, as if some invisible mechanism redistributes thermal energy with impossible efficiency. The temperature uniformity cannot be explained by atmospheric circulation alone. Even Venus, with its crushing carbon dioxide atmosphere and runaway greenhouse effect, maintains temperature differences of several hundred degrees between equatorial and polar regions. The 3I Atlas inner planet achieves thermal equilibrium across hemispheres that receive stellar radiation differing by infinite ratios, the day side basking in perpetual noon, while the night side experiences eternal midnight. The required heat transport would demand atmospheric winds exceeding the speed of sound, yet spectroscopic observations detect no evidence of such violent weather systems. The middle planet exhibits thermal anomalies that challenge fundamental assumptions about radiative energy balance. Its surface temperature remains constant at 340 Kelvin, warm enough to maintain liquid water, despite receiving stellar radiation that should heat it to barely 280 Kelvin. The excess thermal energy amounts to 40% more than the planet receives from stellar heating, suggesting internal heat sources that exceed the gravitational energy release from planetary formation and radioactive decay combined. The planet glows with its own thermal radiation like a miniature star, yet shows no signs of the geological activity that should accompany such enormous internal energy generation. The outermost world presents perhaps the most puzzling thermal signature of all. Despite its distance from the central star, where stellar heating should maintain surface temperatures below 200 Kelvin, infrared observations detect thermal emissions corresponding to a global average temperature of 290 Kelvin, nearly as warm as Earth's surface. The planet receives less than 5% of Earth's solar flux, yet maintains surface conditions that could support liquid water oceans under appropriate atmospheric conditions. The required internal heat source exceeds the planet's total gravitational binding energy, suggesting thermal processes that operate beyond the scope of conventional planetary physics. Thermal infrared mapping reveals that all three planets exhibit heat distribution patterns that correlate with no known geological or atmospheric process. Rather than the random patchwork of hot and cold regions expected from volcanism, impact heating, or atmospheric circulation. The thermal maps display organized patterns that repeat with periodicities matching the orbital resonances between the planets. Hotspots appear and disappear in synchronized cycles, as if the planetary heat sources respond to gravitational tidal forces or electromagnetic coupling between the worlds. The synchronized thermal variations suggest that the planets exchange energy through mechanisms that operate faster than thermal conduction or atmospheric transport. When the inner planet's temperature increases during particular orbital configurations, the middle and outer planets simultaneously experience corresponding thermal changes, despite the vast distances separating them and the multi-day light travel times that should delay any electromagnetic communication. The thermal coupling operates instantaneously across astronomical distances, implying energy transfer processes that transcend the speed of light limitations of conventional physics. Spectroscopic analysis of the thermal emissions reveals blackbody spectra that deviate subtly but consistently from the Planck distribution expected for objects at the observed temperatures. The deviations appear in specific wavelength bands that correspond to vibrational and rotational energy levels of common atmospheric molecules. But the intensity ratios suggest population distributions that violate thermal equilibrium assumptions. The planetary surfaces appear to emit thermal radiation as if matter exists in excited quantum states that should decay within microseconds under normal conditions. The thermal anomalies become even more mysterious when compared with theoretical models of planetary cooling. Standard calculations predict that planets of the observed sizes and compositions should have completed their initial thermal contraction within the first 10 million years after formation, settling into steady states where internal heat generation balances thermal radiation to space. The 3I Atlas planets continue generating excess thermal energy after tens of millions of years, as if powered by energy sources that operate independently of gravitational potential energy and radioactive decay. Some theoretical models propose exotic heating mechanisms to explain the thermal signatures, gravitational wave interactions, dark matter annihilation, or coupling with quantum vacuum fluctuations. However, the required energy densities exceed observational limits from other astrophysical phenomena by orders of magnitude. Alternative proposals invoke modifications to thermodynamic laws under extreme gravitational or electromagnetic conditions, but the 3I Atlas system shows no evidence of the exotic space-time curvature or field strengths that would permit such departures from established physics. The thermal emission spectra exhibit time-variable components that suggest the heating mechanisms respond to external influences on timescales ranging from hours to years. During certain orbital configurations, the thermal output from all three planets increases simultaneously, while other alignments produce coordinated decreases in planetary temperatures. These variations follow no pattern predicted by tidal heating, stellar irradiation changes, or electromagnetic induction from the variable stellar magnetic field. Long-term monitoring reveals that the planetary thermal emissions exhibit slow secular changes that correlate with no known astrophysical process. Over decades of observation, the excess thermal energy from each planet has increased by several percent, suggesting that whatever mechanisms power these worlds grow stronger with time rather than weaker. Conventional heat sources should decay exponentially as gravitational contraction slows and radioactive isotopes undergo nuclear decay. Yet the 3I Atlas thermal anomalies intensify with the patience of geological time. The atmospheric greenhouse effects on all three planets operate with efficiencies that exceed theoretical maxima for known greenhouse gases. Even under the most extreme assumptions about atmospheric composition and pressure, conventional greenhouse warming cannot account for the observed surface temperatures. The atmospheres trap and redistribute thermal energy with nearly perfect efficiency, suggesting radiative transfer processes that violate detailed balance requirements and approach thermodynamic impossibilities. Only took impossible heat distribution to rewrite planetary thermodynamics textbooks. Only needed thermal coupling across astronomical distances to suggest that energy transport in the 3I Atlas system operates by mechanisms faster than light and more efficient than conduction. Only required synchronized temperature variations to whisper that cosmic thermal processes can achieve coordination that transcends the comfortable boundaries of heat transfer theory. The three worlds continue radiating their excess thermal energy into the cosmic void. Each infrared photon, a gentle reminder that planetary heat engines can operate by principles more subtle and strange than human thermodynamics has yet discovered. The isotopic signatures detected in the atmospheres and surface materials of the 3I Atlas planets tell a story that contradicts everything astronomers know about stellar nucleosynthesis and galactic chemical evolution. Spectroscopic analysis reveals abundances of heavy elements, particularly iron-60, aluminum-26, and calcium-41 that should not exist in detectable quantities around such a young star. These radioisotopes possess half-lives ranging from hundreds of thousands to millions of years, meaning they decay to undetectable levels within relatively short cosmic timescales. Their presence in the 3I Atlas system suggests recent exposure to nucleosynthetic processes that typically occur only in the cores of massive stars or during supernova explosions. The iron-60 concentrations exceed galactic background levels by factors of thousands. This isotope forms exclusively in the silicon-burning shells of stars more massive than 20 solar masses, and gets dispersed into the interstellar medium only when these massive stars explode as supernovae. The half-life of iron-60, approximately 2.6 million years, means that detectable quantities can persist only if produced within the very recent past on astronomical timescales. The 3I Atlas system shows iron-60 abundances that would require supernova detonations within 10 light-years of the system within the past few million years. However, no evidence exists for recent supernova activity in the stellar neighborhood surrounding 3I Atlas. The local interstellar medium shows no signs of supernova shock waves, neutron star remnants, or the characteristic X-ray emissions that mark recent stellar explosions. The system appears to sit in a quiet region of the galaxy, far from the star-forming regions and massive stellar associations where supernovae typically occur. The isotopic evidence demands nearby supernova activity that left no other observable traces in the surrounding cosmic environment. The aluminum-26 signatures present an even deeper mystery. This isotope forms in the hydrogen-burning shells of massive stars and gets ejected during stellar winds and supernova explosions, but it also gets produced in smaller quantities during nova explosions and cosmic ray interactions with interstellar dust. The 3I Atlas planets show aluminum-26 abundances that require continuous production and incorporation over millions of years, as if the system experienced repeated exposure to multiple nucleosynthetic sources throughout its formation history. The calcium-41 detections violate fundamental assumptions about cosmic ray interactions and galactic chemical evolution. This isotope forms primarily through cosmic ray spallation high-energy particles, smashing into heavier nuclei and fragmenting them into lighter elements. The production rates depend on cosmic ray fluxes and target material compositions in ways that astronomers understand with considerable precision. The observed calcium-41 abundances in the 3I Atlas system exceed theoretical production rates by factors of hundreds, suggesting cosmic ray environments more intense than anything observed elsewhere in the galaxy. Carbon isotope ratios provide additional evidence for anomalous nucleosynthetic histories. The ratio of carbon-12 to carbon-13 in planetary atmospheres differs significantly from solar system values, indicating formation from materials that experienced different stellar processing environments. The carbon signatures suggest that the planetary building blocks formed in regions of the galaxy with stellar populations, metallicities, and nucleosynthetic yields fundamentally different from our solar neighborhood. Yet stellar population synthesis models predict uniform isotopic compositions across galactic regions with similar ages and metallicities. Oxygen isotope anomalies compound the mystery of the system's chemical evolution. The 3-isotope plot of oxygen-16, oxygen-17, and oxygen-18 ratios reveals compositions that fall along mass-dependent fractionation lines characteristic of high-temperature processing in stellar environments. These signatures typically arise from gas phase chemistry in stellar atmospheres or supernova shock fronts, yet they appear in solid planetary materials that formed at the relatively low temperatures of protoplanetary disk conditions. The isotopic evidence suggests that solid matter in the 3I Atlas system retains memory of high-energy processes that occurred before planetary accretion. The rare Earth element patterns detected through high-resolution spectroscopy exhibit abundant signatures that match no known stellar nucleosynthetic process. Elements like europium, gadolinium, and terbium, which form exclusively through rapid neutron capture processes during supernova explosions, appear in ratios that differ from both solar system values and theoretical R-process predictions. The abundance patterns suggest exposure to neutron flux environments with densities and temporal evolution profiles that exist nowhere in current models of stellar evolution and explosion dynamics. Helium isotope ratios provide evidence for interaction with cosmic environments that operated by different nuclear physics than contemporary stellar processes. The ratio of helium-3 to helium-4 in planetary atmospheres exceeds primordial Big Bang nucleosynthesis values while falling short of contemporary cosmic ray production rates. The helium signatures suggest that the 3I Atlas system formed from materials that experienced nuclear processing under conditions that existed in the early universe but no longer operate in the current galactic environment. The isotopic anomalies extend beyond individual elements to include molecular species that retain signatures of their formation environments. Water vapor in planetary atmospheres shows deuterium enrichments that exceed interstellar ice values by factors of 10, while methane exhibits carbon isotope signatures characteristic of thermochemical processing at temperatures exceeding 1000 Kelvin. These molecular isotopic signatures suggest that volatile compounds in the 3I Atlas system form through pathways that differ fundamentally from solar system analog processes. Temporal variations in isotopic compositions reveal that the anomalous signatures change on timescales of years to decades rather than the millions of years expected for normal radioactive decay or cosmic ray processing. Some isotope ratios appear to oscillate with periodicities that correlate weakly with planetary orbital periods, suggesting that the nucleosynthetic anomalies respond to gravitational or electromagnetic influences within the system itself. The isotopic compositions appear to reflect ongoing nuclear processes rather than ancient formation signatures frozen into planetary materials. Mass spectrometric analysis of atmospheric constituents reveals the presence of isotopes that should not exist under normal cosmic conditions. Elements like technetium-99 and promethium-147, which have no stable isotopes and decay completely within millions of years, appear in trace quantities that require continuous production through unknown nuclear processes. The detection of these artificial isotopes suggests that the 3I Atlas system maintains active nucleosynthetic sources that operate independently of stellar fusion or cosmic ray interactions. Only took impossible isotope ratios to challenge fundamental assumptions about galactic chemical evolution and stellar nucleosynthesis. Only needed traces of elements that should not exist to suggest that nuclear processes in the 3I Atlas system operate by mechanisms beyond terrestrial physics. Only required chemical signatures of elsewhere to whisper that matter itself can retain memories of cosmic environments that transcend the comfortable boundaries of nuclear astrophysics. The planets continue their ancient dance while carrying in their atmospheres and crusts the chemical echoes of stellar processes that never occurred. Isotopic signatures that tell stories of nuclear physics operating under rules more subtle and strange than human science has yet discovered. The three worlds of 3I Atlas circle their star at distances that should subject them to tidal forces capable of tearing planets apart, yet they show no signs of the heating, deformation, or orbital decay that such gravitational stress should produce. The inner planet orbits at barely 6 stellar radii, so close that tidal bulges should raise its surface by hundreds of meters twice per orbit, generating frictional heating sufficient to melt solid rock and boil away oceans. Instead, the world maintains a perfectly spherical shape and stable surface temperature, as if the inexorable mathematics of gravitational tides somehow fail to operate in the alien environment of the 3I Atlas system. Tidal heating calculations predict that the inner planet should generate internal thermal energy exceeding the total power output of human civilization by factors of billions. The gravitational flexing caused by orbital motion around the star should compress and stretch the planetary interior with sufficient violence to maintain molten mantles and create volcanic activity that resurfaces the entire world every few thousand years. Thermal infrared observations detect no evidence of such heating, no volcanic hotspots, no resurfacing events that would mark the release of tidal energy through geological processes. The precise measurement of orbital periods reveals another impossibility. The planets show no signs of orbital decay despite tidal interactions that should spiral them into their star within millions of years. Tidal forces exchange angular momentum between planetary rotation and orbital motion, gradually slowing planetary spins while shrinking orbital radii. This process operates with mathematical certainty throughout the universe. It synchronizes the Moon's rotation with its orbit around Earth, drives the Martian satellites toward inevitable collision with their planet, and will eventually cause Earth itself to spiral into an aging, expanding sun. Yet the 3I Atlas planets maintain orbital periods stable to nanosecond precision across decades of observation. The inner planet should lose orbital energy and spiral inward at rates measurable over human timescales, but its orbit remains as constant as an atomic clock. The expected orbital decay would amount to several meters per year, easily detectable with modern astronomical techniques, yet no such motion appears in the observational record. The planets appear immune to the gravitational processes that govern every other known planetary system. The absence of tidal heating creates thermal paradoxes that compound the mystery of planetary energy budgets. Without tidal dissipation, the planets should have completed their initial gravitational contraction and cooled to equilibrium temperatures determined solely by stellar heating and internal radioactive decay. The observed thermal emissions exceed these predicted temperatures by factors that require energy sources equivalent to continuous tidal heating. Yet no mechanism exists for such heating in the absence of measurable tidal deformation. Even more puzzling, the planets appear to exchange tidal energy between themselves without experiencing the orbital evolution that such energy transfer should produce. Gravitational interactions between the three worlds create complex tidal patterns that vary with their orbital configurations. Yet these varying tidal forces produce no detectable changes in planetary shapes, rotation rates, or orbital elements. The tidal energy appears to dissipate through pathways that operate outside the framework of conventional gravitational dynamics. Theoretical models of tidal interactions require planetary interiors with mechanical properties that cannot exist under normal conditions. To explain the absence of tidal heating while maintaining the observed orbital stability, the planets would need internal structures with quality factors, measures of mechanical energy dissipation that exceed the theoretical maximum for any known material by orders of magnitude. The required mechanical properties approach those of perfect elastic solids that respond to stress without any energy loss. Yet such materials cannot exist at the temperatures and pressures of planetary interiors. The tidal restraint extends beyond individual planets to include the electromagnetic interactions that should couple planetary magnetospheres with tidal forces. In gas giant systems like Jupiter and Saturn, tidal interactions between planets and their moons create complex electromagnetic phenomena as magnetic field lines stretch and reconnect during orbital motion. The 3I Atlas system should exhibit similar magnetospheric tidal effects, yet radio observations detect no evidence of the expected electromagnetic signatures of tidal magnetic field interactions. Spectroscopic monitoring of atmospheric tides reveals another anomaly in the system's gravitational behavior. Planetary atmospheres typically experience tidal bulges that create pressure variations, temperature oscillations, and wind patterns that correlate with orbital motion and tidal forcing. The 3I Atlas planets show atmospheric pressure variations that follow no tidal pattern, as if their atmospheres remain isolated from the gravitational influences that should dominate their dynamics. The absence of tidal evolution conflicts with direct observational evidence for strong gravitational interactions between the system's components. Precise astrometry reveals that the planets perturb each other's orbits through gravitational forces that should also produce measurable tidal effects. The same gravitational fields that create orbital perturbations should inevitably generate tidal deformation. Yet only the orbital effects appear in the observational data while tidal signatures remain completely absent. Long-term orbital monitoring reveals that the gravitational interactions between planets follow Newton's law of universal gravitation with perfect precision for orbital motion, while apparently ignoring the tidal components of the same gravitational fields. The inverse square law operates normally for forces that accelerate planetary centers of mass, but seems to vanish for forces that should deform planetary shapes or transfer rotational energy between spin and orbital motion. Some theoretical proposals invoke exotic modifications to general relativity that could suppress tidal effects while preserving orbital dynamics. But such modifications would require space-time curvature or gravitational field configurations that produce observable signatures in other aspects of the system's behavior. The 3i Atlas system shows no evidence of the extreme gravitational environments that would permit departures from standard tidal theory. Alternative models propose that the planets possess internal structure or composition that perfectly compensates for tidal heating through unknown cooling mechanisms. Such thermal balance would require heat transport processes that operate with impossible efficiency, removing tidal energy from planetary interiors at exactly the rate required to maintain thermal equilibrium. The necessary heat transport would exceed the efficiency of thermal conduction by factors of millions, while leaving no trace in surface geology or atmospheric dynamics. Only took the absence of inevitable tidal heating to challenge fundamental assumptions about gravitational interactions and energy dissipation. Only needed perfect orbital stability to suggest that tidal forces in the 3i Atlas system operate by rules that transcend Newtonian mechanics. Only required gravitational restraint to whisper that cosmic clockwork can achieve precision that exceeds the chaos of normal tidal evolution. The three worlds continue their eternal dance at impossible distances, each orbit a quiet demonstration that gravitational forces can maintain perfect restraint when the universe chooses to suspend the inexorable mathematics of tidal destruction. The migration history of the 3i Atlas planets tells a story that contradicts every prediction of planetary formation theory, a tale written in the absence of evidence that should mark billions of years of gravitational wandering through their stellar system. Standard models predict that planets form at various distances from their star and then migrate inward or outward through interactions with the protoplanetary disk, scattering debris and carving gaps that persist long after the original gas and dust have dissipated. Yet the 3i Atlas system shows no trace of this expected migration pathway, as if the planets materialized in their current orbits without ever having existed anywhere else. The debris disk surrounding the central star exhibits a pristine structure that should have been destroyed by migrating planets within the first few million years of system evolution. Infrared observations reveal multiple rings of dust and rocky debris at distances ranging from 10 to 100 astronomical units from the star well beyond the current planetary orbits. These debris rings maintain sharp edges and complex fine structure that would be smeared and scattered by the gravitational perturbations of planets moving through the disk during migration episodes. Each debris ring corresponds to distances where theoretical models predict that planets should have formed before migrating to their current positions. The inner planets should have originated in the asteroid belt region and spiraled inward through disk interactions, while the outer planet should have migrated outward from closer to the star. Such migration would scatter debris, create gaps in the disk structure, and leave behind gravitational signatures that persist for billions of years. Instead, the debris rings appear untouched, as if no massive objects ever passed through their orderly arrangement. The chemical composition of debris particles, determined through spectroscopic analysis of reflected starlight, reveals materials that should have been redistributed throughout the system during planetary migration. Silicate dust in the inner rings shows no contamination from water ice or organic compounds that would have been scattered inward from the outer system during planetary migration. Similarly, The outer debris rings contain no rocky material or refractory elements that should have been ejected outward by migrating planets. Each ring maintains a chemically pure composition that reflects its current distance from the star. Gravitational modeling reveals that the current planetary configuration could not have formed through any known migration pathway without leaving detectable traces in the debris disk structure. Simulations that begin with planets at their formation locations and migrate them to their observed positions invariably predict debris disk disruption that conflicts with the observed pristine structure. Alternative models that form planets in situ at their current locations cannot reproduce the observed orbital resonances and system architecture. The absence of migration signatures extends to the broader stellar environment surrounding the 3 Atlas system. Planetary migration typically ejects substantial amounts of material into interstellar space, creating comet clouds, rogue asteroids, and stellar debris streams that remain detectable for millions of years. Deep astronomical surveys detect no such material in the vicinity of 3I Atlas, despite sensitivity limits that should reveal migration debris from systems hundreds of light-years away. The planetary mass distribution provides additional evidence against conventional migration scenarios. In systems that underwent extensive migration, planetary masses typically correlate with final orbital positions in ways that reflect the efficiency of disk interactions and gravitational scattering. The 3I Atlas planets show no such correlations. Their masses appear randomly distributed with respect to their orbital distances, as if each world formed independently without interacting with its companions during their evolutionary history. Isotopic analysis of atmospheric constituents reveals chemical signatures that conflict with migration predictions. Planets that migrated through different temperature regions of their protoplanetary disk should exhibit atmospheric compositions that blend materials from multiple formation zones. The 3I Atlas planets show isotopic ratios and molecular abundances that suggest formation from chemically uniform materials, as if each world condensed from disk material with composition determined solely by its current distance from the star. The orbital eccentricities and inclinations of all 3 planets remain extraordinarily low despite the gravitational perturbations that should accompany migration through a debris-rich environment. Planetary migration typically excites orbital eccentricities and inclinations through close encounters with planetesimals and gravitational interactions with disk material. The perfectly circular, coplanar orbits observed in the 3I Atlas system suggest evolution in a dynamically cold environment, free from the gravitational chaos that marks normal migration processes. Temporal constraints from stellar evolution modeling compound the migration mystery. The central star's age and evolutionary state indicate that substantial planetary migration should have occurred within the past few million years, recent enough that migration signatures should remain clearly visible in debris disk structure and orbital dynamics. Yet, no evidence exists for such recent migration. Despite theoretical predictions that planets in close-packed resonant systems typically achieve their final configurations through migration processes that operate over precisely these timescales. The angular momentum distribution within the system reveals patterns that contradict all known migration mechanisms. Planetary migration typically redistributes angular momentum between planets and their surrounding disk material, creating characteristic signatures in the final orbital architecture. The 3I Atlas system exhibits angular momentum patterns that match no migration model while perfectly conserving the total rotational energy expected for planets that formed in their current locations without ever moving. Some theoretical models propose that the planets form through direct gravitational collapse from disk instabilities rather than through accretion and migration processes. However, Such formation mechanisms require disk masses and instability conditions that conflict with observational constraints on protoplanetary disk properties around young stars. Alternative proposals invoke exotic physics-modified gravity, dark matter interactions, or quantum mechanical effects on astronomical scales, but such mechanisms leave no other observable signatures in the system's behavior. The missing migration story extends to the finest details of orbital dynamics. Planetary migration creates specific patterns in orbital period ratios, eccentricity distributions, and resonant angles that astronomers use to reconstruct the migration history of exoplanetary systems. The 3I Atlas orbital elements exhibit none of these expected patterns, instead showing mathematical relationships that appear designed to optimize stability rather than arising from chaotic migration processes. Only took the absence of inevitable debris trails to challenge fundamental assumptions about planetary system architecture and evolution. Only needed pristine disk structure to suggest that planetary formation in the 3I Atlas system operated without the migration processes that shape every other known planetary system. Only required a missing story to whisper that cosmic evolution can proceed by pathways more direct and mysterious than current planetary formation theory encompasses. The three worlds continue their perfect dance while the debris rings maintain their undisturbed order. Each pristine orbit a gentle reminder that planetary systems can achieve architectural precision without ever experiencing the chaotic wandering that marks normal cosmic evolution. The surfaces of all three worlds in the 3I Atlas system exhibit a geological serenity that defies 4 billion years of cosmic bombardment, their pristine terrains unmarked by the impact craters that should record eons of collisions with asteroids, comets, and interplanetary debris. High-resolution imaging reveals landscapes of impossible smoothness, with crater densities so low they suggest surface ages measured in thousands rather than billions of years. Yet, independent evidence from atmospheric evolution and orbital dynamics confirms that these worlds have circled their star since the system's formation, creating a temporal paradox that challenges fundamental assumptions about solar system evolution and planetary surface processes. The absence of impact craters cannot be explained by atmospheric protection or geological resurfacing. The inner planet, with its tenuous atmosphere and tidally locked rotation, should display a heavily cratered landscape similar to Mercury's ancient surface. Instead, optical and radar observations reveal terrain features that appear freshly formed, with no sign of the circular scars that mark billions of years of cosmic bombardment. The few crater-like features that do exist show morphologies inconsistent with impact formation, too shallow, too symmetrical, lacking the characteristic central peaks and ejecta blankets that mark genuine impact structures. The middle planet presents an even greater mystery. Its substantial atmosphere should protect against smaller impactors while allowing larger objects to reach the surface and create craters tens of kilometers across. Atmospheric entry calculations predict that objects larger than 1 kilometer in diameter should survive atmospheric passage and excavate craters comparable to Earth's Chicxulub impact structure. Yet spectroscopic analysis of atmospheric composition reveals no evidence of impact-generated dust, vaporized rock, or chemical signatures that would mark recent large-scale collisions. The outermost world shows surface features that suggest active geological processes capable of erasing impact craters, yet exhibits no signs of the volcanism, tectonism, or atmospheric dynamics that typically drive such resurfacing. Thermal infrared observations detect no volcanic hotspots, no evidence of recent lava flows or ash deposits that could bury impact craters beneath fresh geological material. The surface appears geologically dead, yet somehow maintains the youthful appearance of a world that has never experienced significant bombardment. Debris disk observations reveal abundant populations of asteroids and comets throughout the 3I Atlas system, more than sufficient to create heavily cratered planetary surfaces through billions of years of impacts. The debris particles exhibit orbital distributions and size-frequency relationships similar to those in the solar system, where such populations have pummeled planetary surfaces since formation. Impact rate calculations based on debris populations predict crater densities exceeding lunar highlands levels, yet the planetary surfaces show virtually no impact scarring. The absence of impact debris represents another impossible aspect of the system's geology. Large impacts typically scatter rocky material across planetary surfaces and into space, creating secondary crater chains and debris fields that remain detectable for billions of years. Impact ejecta should contaminate surface compositions with materials from impactor bodies, creating chemical signatures that reflect the bombardment history. Spectroscopic analysis of planetary surfaces reveals no such contamination. Surface compositions appear chemically pure, as if no foreign material has ever mixed with indigenous rocks. The missing bombardment history extends to atmospheric evolution, where impact events should have played crucial roles in atmospheric loss and chemical modification. Large impacts strip away atmospheric gases through shock heating and impact ejecta, while also delivering volatile compounds from cometary bodies. The atmospheric compositions of all three planets show no evidence of impact-driven evolution, no noble gas signatures from cometary impacts, no isotopic fractionation from atmospheric stripping, no chemical modifications that would mark billions of years of bombardment. Cratering chronology models based on lunar and terrestrial impact records predict specific relationships between crater size distributions and surface ages that should apply universally to rocky planets. The 3I Atlas surfaces violate these relationships completely. The few observed crater-like features exhibit size distributions that match no known bombardment population or impact process. The crater statistics suggest exposure ages of mere thousands of years. Yet other geological evidence confirms planetary ages measured in billions of years. The absence of impact heating signatures compounds the geological mysteries. Large impacts release enormous amounts of kinetic energy, melting and vaporizing target rocks to create distinctive geological formations, shock metamorphosed minerals, impact glass, and pressure-modified crystal structures that persist for billions of years. High-resolution spectroscopy detects no evidence of such impact-generated materials on any of the three planetary surfaces, as if the worlds have never experienced the violent energy release of high-velocity collisions. Some theoretical models propose that electromagnetic fields or exotic gravitational effects could deflect incoming impactors away from planetary surfaces, but such protective mechanisms would require field strengths or space-time curvatures that should produce observable signatures in other aspects of system behavior. The 3I Atlas system shows no evidence of the extreme electromagnetic or gravitational environments that could provide planetary protection against cosmic bombardment. Alternative proposals invoke rapid geological processes that could erase impact craters faster than they form. But such accelerated geology would require energy sources and heat transport mechanisms that far exceed those available on normal planetary bodies. The required resurfacing rates would demand volcanic activity or tectonic processes operating at intensities that should be easily detectable through thermal infrared observations and seismic monitoring. The temporal paradox deepens when astronomers consider the debris disk evolution that should accompany normal impact processes. Planetary bombardment typically clears debris from inner solar system regions through gravitational scattering and impact accretion, creating age-dependent changes in debris disk structure that remain observable for billions of years. The 3I Atlas debris disks show no evidence of such clearing. Their structure appears unchanged by the planetary bombardment that should have occurred throughout system evolution. Gravitational modeling reveals that the current debris populations should deliver impactors to planetary surfaces at rates sufficient to create observable craters within human timescales. The absence of fresh crater formation during decades of astronomical monitoring suggests that either the bombardment rate has decreased to essentially zero, an impossibility given the observed debris populations, or some unknown mechanism prevents impacts from occurring despite the continued presence of potential impactors throughout the system. Only took the absence of inevitable impact craters to challenge fundamental assumptions about solar system evolution and planetary surface processes. Only needed pristine geological terrains to suggest that cosmic bombardment in the 3I Atlas system operates by rules that transcend normal impact dynamics. Only required missing evidence of 4 billion years of cosmic violence to whisper that planetary surfaces can maintain eternal youth through mechanisms more mysterious than geological resurfacing or atmospheric protection. The three worlds continue their ancient dance while maintaining surfaces of impossible serenity, each unmarked terrain a gentle demonstration that cosmic bombardment can somehow pause its inexorable reign of destruction when the universe chooses to preserve planetary perfection. Deep space gravitational wave detectors scattered across the galaxy capture minute ripples in space-time emanating from the 3I Atlas system. Faint distortions in the fabric of reality itself, that whisper of mass distributions and gravitational field geometries that challenge every principle of planetary structure and composition. These space-time tremors arrive at Earth with frequencies and amplitudes that suggest the three worlds possess internal mass arrangements fundamentally different from any known type of planetary body. Their gravitational signatures encoding mysteries that transcend the comfortable boundaries of Newtonian mechanics and general relativity. The gravitational wave emissions exhibit periodicities that correlate weakly with planetary orbital motions, but never quite synchronize with the observed orbital periods. The strongest signals repeat every 4.2217 Earth days, tantalizingly close to the inner planet's 4.2-day orbit, but offset by precisely 17 minutes in a pattern that remains constant across years of detection. These temporal discrepancies suggest that the gravitational wave sources move independently of the planetary surfaces themselves, perhaps reflecting internal mass redistributions or exotic matter configurations that operate on slightly different timescales than orbital motion. Standard gravitational wave theory predicts that planetary bodies should produce no detectable space-time ripples except during catastrophic events like collisions or tidal disruption. The steady, low-amplitude signals from 3I Atlas suggest ongoing gravitational processes that operate continuously rather than episodically, perhaps mass currents within planetary interiors or exotic matter phases that create time-varying gravitational fields without corresponding changes in external gravitational attraction. The frequency spectrum of the gravitational emissions reveals fine structure that matches no known source mechanism. Instead of the broad-band noise expected from chaotic internal processes or the narrow-band signals characteristic of rotating compact objects, the 3I Atlas gravitational waves exhibit complex harmonic relationships that suggest organized, coherent sources of space-time curvature. The harmonic patterns repeat with mathematical precision that exceeds the stability of atomic clocks, indicating gravitational field oscillations that maintain phase coherence across astronomical timescales. Interferometric analysis of signals detected simultaneously by multiple gravitational wave observatories reveals that the space-time distortions propagate with velocities that differ subtly but measurably from the speed of light. Classical general relativity predicts that gravitational waves should travel at exactly the speed of light in vacuum, with any deviation indicating modifications to Einstein's field equations or the presence of exotic matter that couples to gravity through unknown mechanisms. The observed propagation delays suggest that space-time itself possesses dispersive properties in the vicinity of the 3I Atlas system. The polarization characteristics of the gravitational waves exhibit patterns that require more than the two polarization states allowed by standard general relativity. Einstein's theory predicts that gravitational waves should possess only plus and cross polarizations, specific patterns of space-time stretching and compression that create characteristic signatures in interferometric detectors. The 3I Atlas signals show evidence for additional polarization modes that would require modifications to the fundamental structure of space-time or the presence of gravitational fields that operate by principles beyond conventional relativity. Detailed analysis of signal amplitudes reveals that the gravitational wave power output from each planet exceeds theoretical limits for any known source mechanism by factors of millions. The required energy generation would demand mass-energy conversion rates comparable to nuclear fusion reactors. Yet the planets show no signs of the thermal emissions or radiative signatures that should accompany such enormous energy release. The gravitational waves appear to carry away energy that comes from nowhere, while leaving no trace in other observable properties of the planetary system. The temporal evolution of gravitational wave amplitudes suggests that the emission mechanisms strengthen over time rather than weakening through energy dissipation. Conventional sources of gravitational radiation rotating neutron stars, in spiraling binary systems, oscillating black holes gradually lose energy through gravitational wave emission and consequently decrease their signal strength over time. The 3I Atlas emissions show the opposite behavior, growing stronger with the patience of geological time, as if powered by energy sources that increase rather than diminish. Cross-correlation analysis between gravitational wave signals and other observable properties of the system reveals unexpected relationships that suggest fundamental coupling between space-time geometry and electromagnetic phenomena. Changes in gravitational wave amplitude correlate with variations in radio emissions, atmospheric compositions, and thermal signatures in ways that imply gravitational fields directly influence electromagnetic processes through mechanisms beyond the weak coupling predicted by standard physics. The gravitational wave memory effect, permanent space-time distortions that persist after gravitational wave passage, creates cumulative geometric changes in local space-time that should be detectable through precision astrometry and atomic clock networks. The 3I Atlas system appears to generate memory effects that accumulate over years of observation, gradually modifying the geometric properties of space in ways that influence the propagation of light and the flow of time itself throughout the stellar neighborhood. Some theoretical models propose that the gravitational anomalies arise from interactions with dark matter concentrations or exotic field configurations that exist only in the extreme gravitational environment surrounding young stellar systems. However, the required dark matter densities or field strengths exceed observational limits from galaxy dynamics and cosmological structure formation by orders of magnitude. Alternative explanations invoke quantum mechanical effects on macroscopic scales or modifications to general relativity that operate only under specific conditions found in the 3A Atlas system. The gravitational wave data suggests that each planet possesses internal mass distributions that cannot be reconciled with any combination of known materials under normal conditions. The inferred density profiles require central cores with negative mass densities or exotic matter phases that violate energy conditions fundamental to general relativity. Such configurations should create gravitational repulsion rather than attraction. Yet the planets maintain normal orbital dynamics that follow Kepler's laws with perfect precision. Attempts to model the internal structure necessary to produce the observed gravitational wave signatures require planetary cores composed of materials that exist only in theoretical proposals, strange matter, dark energy condensates, or microscopic black holes that somehow remain stable against Hawking radiation and gravitational collapse. The required exotic matter would need to maintain coherent quantum states across planetary scale distances while interacting gravitationally but not electromagnetically with ordinary matter. Only took faint space-time ripples to challenge fundamental assumptions about planetary structure and gravitational field generation. Only needed minute distortions in the fabric of reality to suggest that mass distributions in the 3i Atlas system operate by principles beyond general relativity. Only required gravitational whispers to hint that cosmic architecture can achieve geometric precision that transcends the comfortable boundaries of space-time physics. The gravitational waves continue their journey across the galaxy. Each ripple in space-time, a gentle reminder that planetary bodies can generate gravitational fields that operate by rules more subtle and strange than Einstein's equations have yet discovered. The geological timescales revealed by surface features across all three worlds of 3i Atlas create a temporal paradox that fragments the very concept of planetary evolution, where some processes appear to operate at impossible speeds, while others unfold with equally impossible slowness. Mountain ranges that should require hundreds of millions of years to form through tectonic processes show evidence of completion within mere thousands of years, while impact basins that should be erased by erosion within millions of years persist unchanged across geological eras that span billions of years. The inner planet displays volcanic formations that exhibit crystalline structures requiring cooling periods of millions of years. Yet isotopic dating of the same rock formations suggests ages measured in thousands of years. The contradiction defies fundamental principles of igneous petrology. Large crystals form only through slow cooling that allows atoms time to arrange themselves into ordered lattice structures. Yet, the observed crystal sizes would require cooling rates that differ from measured formation ages by factors of thousands. The rocks appear to remember a thermal history that never occurred. Mountain chain morphologies on the middle planet reveal tectonic processes that violate everything geologists understand about crustal deformation and orogenic evolution. The observed mountain heights and structural geometries require crustal shortening and uplift processes that should operate over timescales of tens of millions of years. Yet spectroscopic analysis of mountain composition reveals mineral assemblages that could form only under pressure and temperature conditions lasting mere centuries. The mountains exist in a state of temporal impossibility, too young to have reached their observed structural maturity, too old to maintain their observed mineral compositions. Valley networks carved by liquid water flow exhibit dendritic patterns that suggest millions of years of gradual erosion. Yet, atmospheric evolution models indicate that surface conditions suitable for liquid water existed for less than 10,000 years during the entire history of each planet. The erosional features record hydrological processes that operated for far longer than the atmospheric conditions that could support them, creating geological evidence for water cycles that transcend the physical constraints of planetary climate evolution. Sedimentary rock formations display layered structures that represent millions of depositional cycles, each thin stratum marking seasonal or annual changes in environmental conditions. Yet, radiometric dating of organic materials within the sediments yields formation ages that span only thousands of years, compressing geological time by factors that challenge fundamental assumptions about sedimentary accumulation rates. The rocks contain more history than time allows, each layer a testament to processes that operate by temporal rules beyond terrestrial geology. The surface features exhibit preservation states that violate basic principles of geological aging and modification. Crater chains, tectonic scarps, and volcanic flow fronts maintain morphological details that should be erased by erosion within millions of years. Yet independent age determinations confirm that these features formed billions of years ago. The landscapes appear frozen in time, preserving geological youth across cosmological ages through mechanisms that transcend normal weathering and surface modification processes. Impact crater morphologies, where they exist at all. Display degradation states that correlate with no known model of geological or atmospheric erosion. Some craters appear freshly formed despite radiometric ages exceeding billions of years, while others show advanced degradation despite formation ages measured in thousands of years. The crater degradation appears to operate independently of time, following patterns that suggest erosional processes governed by unknown physical principles. Volcanic flow sequences exhibit temporal relationships that defy stratigraphic principles established through centuries of geological observation. Lava flows that should represent the most recent volcanic activity, based on their position above older formations, yield radiometric ages that predate the underlying rocks by millions of years. The geological column appears temporally inverted, with younger rocks beneath older formations in configurations that violate gravitational settling and depositional sequence logic. Mineral assemblages within metamorphic rock formations indicate pressure and temperature histories that require burial and exhumation cycles operating over timescales ranging from thousands to billions of years within the same rock units. Individual mineral grains preserve evidence of metamorphic events separated by geological ages, yet coexist in textural equilibrium that should develop only through simultaneous formation under identical conditions. The rocks record multiple, incompatible thermal histories within single-hand specimens. Erosional landforms exhibit development stages that correlate with no known relationship between erosional processes and elapsed time. River valleys show maturity levels that typically require millions of years to achieve, yet exist in terrains with exposure ages measured in thousands of years. Conversely, some landscapes show negligible erosional modification despite exposure ages exceeding billions of years, as if erosional processes operate by temporal rules that bear no relationship to normal geological time. The paleomagnetic signatures preserved in rock formations reveal temporal evolution of planetary magnetic fields that violate fundamental principles of dynamo theory and core evolution. Magnetic field reversals appear to occur on timescales of decades rather than the hundreds of thousands of years observed on Earth. Yet the magnetic intensity variations suggest core cooling and crystallization processes that should operate over billions of years. The magnetic history appears compressed and extended simultaneously. Geochemical weathering profiles exhibit development patterns that suggest both rapid and impossibly slow chemical alteration processes operating within the same surface materials. Clay mineral assemblages that typically form through millions of years of chemical weathering appear in soils with formation ages measured in centuries, while some rock surfaces show no signs of chemical alteration despite billions of years of exposure to atmospheric and hydrological processes. Surface temperature records preserved in mineral phase relationships and isotopic signatures reveal thermal histories that span timescales from hours to geological eras within individual rock formations. Some thermal events appear to have occurred instantaneously across planetary scale regions, while others show gradual evolution over periods that exceed the age of the entire planetary system. The thermal history appears to operate by temporal rules that permit simultaneous fast and slow processes. Tectonic deformation patterns preserved in rock structures indicate crustal stress fields that changed orientation and magnitude on timescales ranging from years to billions of years. Yet the observed structural geometries require consistent stress orientations maintained over intermediate timescales of millions of years. The structural geology appears to remember multiple, incompatible stress histories that could not have operated sequentially within the observed time constraints. Only took impossible geological timescales to challenge fundamental assumptions about the relationship between time and planetary surface processes. Only needed temporal paradoxes embedded in rock formations to suggest that geological evolution in the 3I Atlas system operates by chronological rules beyond terrestrial geology. Only required shattered clocks to whisper that cosmic time itself can flow at different rates for different processes within the same planetary environment. The three worlds continue their eternal dance while their surfaces preserve geological memories that transcend linear time. Each rock formation, a gentle demonstration that planetary evolution can unfold through temporal pathways more complex and mysterious than human geology has yet discovered. In the vast darkness between the three worlds of 3I Atlas, subtle gravitational perturbations hint at the presence of invisible matter that interacts with ordinary planetary materials through mechanisms that transcend the comfortable boundaries of standard particle physics. Precision astrometry reveals orbital deviations that exceed the gravitational influence of all known system components, planets, debris rings, and central star by margins that suggest substantial quantities of dark matter concentrated within the inner regions of the planetary system, far from the diffuse galactic halo where such exotic matter typically resides. The orbital perturbations exhibit periodicities and amplitudes that correlate with no known source of gravitational influence. The inner planet's orbit precesses at rates that exceed general relativistic predictions by factors of hundreds, while maintaining orbital stability that should be impossible under such strong perturbative forces. The excess precession follows patterns that suggest interaction with a structured dark matter distribution rather than the smooth, isotropic field expected from conventional cosmological dark matter models. Gravitational microlensing observations reveal dark matter concentrations that form coherent structures within the 3I Atlas system rather than the uniform distribution predicted by cosmological simulations. These dark matter clumps appear to maintain stable configurations that orbit the central star independently of the visible planets, creating a hidden planetary system composed of invisible matter that operates by gravitational rules subtly different from ordinary matter dynamics. The dark matter objects exhibit orbital resonances with each other that mirror but do not exactly match the resonances of the visible planets. The interaction between dark matter and ordinary matter appears to violate fundamental assumptions about the nature of dark matter's gravitational coupling. Standard cosmological models predict that dark matter interacts only through gravity, remaining invisible to electromagnetic forces while influencing ordinary matter solely through gravitational attraction. The 3I Atlas system shows evidence for additional interactions. Dark matter appears to transfer momentum and energy to planetary atmospheres through mechanisms that operate faster than gravitational dynamics and leave signatures in atmospheric chemistry and circulation patterns. Atmospheric compositions on all three planets exhibit elemental abundances that require production mechanisms beyond known nuclear processes. Trace quantities of super-heavy elements, atomic nuclei with masses exceeding uranium, appear in atmospheric spectra despite the impossibly short half-lives that should cause such elements to decay within microseconds. The persistence of super-heavy nuclei suggests stabilization through interactions with dark matter particles that modify nuclear physics through unknown coupling mechanisms. The super-heavy elements exhibit isotopic ratios that correlate with dark matter density variations inferred from gravitational perturbations, as if the exotic nuclei form through nuclear processes that respond directly to dark matter concentrations. Some theoretical models propose that dark matter particles can catalyze nuclear reactions or modify fundamental forces within atomic nuclei. But such interactions would require particle physics beyond the standard model and coupling strengths that exceed observational limits from terrestrial particle accelerator experiments. Temporal variations in atmospheric compositions reveal that superheavy element abundances change on timescales that correlate with orbital motion through regions of varying dark matter density. As planets move through their elliptical orbits, they encounter dark matter concentrations that appear to enhance nuclear processes and modify decay rates of unstable isotopes. The nuclear physics appears to respond to dark matter environment in ways that suggest fundamental interactions between exotic matter and atomic structure. The dark matter interactions create thermal signatures that appear in planetary infrared emissions despite the absence of electromagnetic coupling that would permit direct energy transfer. Dark matter concentrations seem to generate heat through gravitational interactions that operate more efficiently than conventional tidal heating or gravitational wave emission. The enhanced heating provides an alternative explanation for the thermal anomalies observed throughout the system, yet requires dark matter interaction cross-sections that exceed cosmological constraints by enormous factors. Radio emissions from the system exhibit modulation patterns that correlate with inferred dark matter orbital periods rather than visible planetary motion. The electromagnetic signals appear to respond to invisible gravitational sources that create time-varying electromagnetic fields through unknown coupling mechanisms. The radio modulations suggest that dark matter can influence electromagnetic phenomena either directly through non-gravitational interactions or indirectly through modification of space-time geometry in ways that affect electromagnetic field propagation. Gravitational wave signals detected from the 3i Atlas system show frequency components that match the orbital periods of inferred dark matter objects rather than visible planets. The space-time distortions appear to arise from dark matter dynamics that operate independently of ordinary matter motion while maintaining gravitational coupling that influences visible system components. The gravitational wave emissions suggest that dark matter can generate space-time curvature through mechanisms beyond simple mass-energy concentration. The dark matter distribution exhibits structural features that mirror but do not exactly match the visible matter architecture of the system. Dark matter appears to form its own planetary analogues, massive, gravitationally bound objects that orbit the central star while remaining completely invisible to electromagnetic observation. These dark matter planets maintain orbital resonances with each other and weak coupling with visible planets that creates the observed gravitational perturbations. Some dark matter models propose that exotic particles can form complex structures analogous to atoms and molecules, potentially allowing dark matter to condense into planetary scale objects with internal structure and dynamics. Such dark matter planets could possess dark matter atmospheres, dark matter geology, and dark matter weather systems that operate parallel to ordinary matter processes while remaining invisible except for their gravitational signatures. The stability of dark matter structures within the 3i Atlas system requires particle physics that differs fundamentally from standard dark matter models. Conventional dark matter candidates weakly interacting massive particles, axions, sterile neutrinos cannot form the coherent, long-lived structures inferred from gravitational observations. The required dark matter physics demands self-interacting particles that can dissipate energy and angular momentum while maintaining stability against gravitational collapse or dispersal. Alternative dark matter models invoke modified gravity theories that could create apparent dark matter signatures through gravitational field configurations that deviate from general relativity under specific conditions. However, such modifications would produce observable signatures in other aspects of system behavior, orbital dynamics, gravitational wave propagation, stellar evolution that do not appear in the observational data. The dark matter fingerprints appear to arise from genuine exotic matter rather than modified gravitational physics. The interaction between dark matter and electromagnetic fields might operate through mechanisms that couple dark matter particles to photons via intermediary fields or virtual particle exchange processes. Such interactions could allow dark matter to influence radio emissions, atmospheric chemistry, and thermal radiation without directly coupling to electromagnetic forces. The required coupling mechanisms would represent entirely new physics beyond both the standard model of particle physics and general relativity. Only took invisible matter to challenge fundamental assumptions about the nature of dark matter and its interactions with ordinary physics. Only needed gravitational fingerprints of exotic particles to suggest that dark matter in the 3I Atlas system operates by rules beyond standard cosmological models. Only required possible evidence of alien particle physics to whisper that the universe contains matter types and interaction mechanisms more subtle and strange than human science has yet discovered. The dark matter continues its hidden dance around the central star while the visible planets trace their impossible orbits. Each gravitational perturbation a gentle reminder that cosmic architecture can transcend the comfortable boundaries between ordinary and exotic matter. The accumulated evidence from decades of observation forces planetary scientists to confront an uncomfortable truth that challenges the very foundations of their discipline: current theoretical models of planetary formation, evolution, and dynamics cannot explain the existence of the 3I Atlas system without invoking physical processes that transcend established scientific understanding. Every aspect of the system, from orbital mechanics to atmospheric chemistry, from thermal evolution to gravitational wave emission, operates by rules that lie beyond the comfortable boundaries of contemporary astrophysics, demanding fundamental revisions to theories that have successfully explained planetary behavior throughout the galaxy. The theoretical crisis extends beyond simple parameter adjustments or model refinements to encompass the basic physical principles that govern planetary systems. The observed phenomena cannot be accommodated through minor modifications to existing theories. They require entirely new frameworks that incorporate physics beyond the standard model of particle interactions and general relativity. The implications ripple through multiple scientific disciplines, challenging assumptions about thermodynamics, gravitational dynamics, electromagnetic theory, and the fundamental nature of space and time. Standard planetary formation models predict that rocky planets form through the gradual accretion of solid materials over tens of millions of years, followed by billions of years of orbital migration, atmospheric evolution, and surface modification. The 3I Atlas system achieved its current configuration in mere millions of years, while maintaining stability characteristics that should develop only over much longer timescales. The formation timeline appears compressed by factors that require accretion, physics operating under entirely different rules than those observed in terrestrial planet formation. The perfect orbital resonances that lock the three planets in their eternal dance should represent the endpoint of long migration histories through protoplanetary disk interactions. Yet, the system shows no evidence of such migration while maintaining resonant relationships that exhibit mathematical precision exceeding anything observed elsewhere in the galaxy. The orbital architecture suggests that planets can somehow choose optimal configurations that minimize gravitational potential energy without experiencing the chaotic evolution that typically shapes planetary system structure. Atmospheric physics models fail to explain the persistence of metallic vapors in planetary atmospheres under conditions where such materials should condense and precipitate within hours. The observed atmospheric chemistry requires physical processes that maintain gaseous metals against gravitational settling while creating circulation patterns that follow magnetic field lines rather than pressure gradients. The atmospheric dynamics appear to operate more like plasma physics than meteorology, yet under conditions where plasma formation should be impossible, thermal evolution models cannot account for the excess heat generation observed throughout the system without invoking energy sources that exceed the total gravitational binding energy of the planets themselves. The required thermal power output demands nuclear processes operating at rates that far exceed radioactive decay or any known nuclear reaction mechanism. The thermal signatures suggest energy generation through exotic physics, perhaps quantum vacuum interactions, dark matter annihilation, or modifications to thermodynamic laws under extreme gravitational conditions. Gravitational wave observations reveal space-time distortions that require mass distributions and field geometries inconsistent with any known form of matter under normal conditions. The inferred planetary interiors would need to contain exotic matter phases that violate energy conditions fundamental to general relativity, while somehow maintaining normal orbital dynamics that follow Kepler's laws with perfect precision. The gravitational wave data suggests that matter itself can exist in states that transcend the comfortable categories of solid, liquid, gas, and plasma. The absence of impact cratering throughout the system challenges basic assumptions about solar system evolution and planetary surface processes. The pristine geological terrains suggest either impossibly rapid resurfacing mechanisms or protective processes that prevent cosmic bombardment without leaving